All right. Does anybody have questions? There have been several good questions during office hours that I might quickly discuss.
I have
Well,
one.
does anybody else have any specific questions?
I calculated for question 105 who's the fastest runner for their class. So when I put who's the fastest runner, do I just put this person the fastest runner because I used standard deviation to calculate it?
Well, you find a z-score because you can say who's the fastest runner with respect to his or her class because they have a higher z-score. Yeah.
Okay.
Z-score gives you relative position of something, relative to what? Relative to their group. So like a group of pianos, you couldn't compare the cost of a piano with the cost of a guitar. They're different things. So I want to compare the cost of a piano to all pianos and the cost of a guitar to all guitars. Okay, do what you got to do. Does anybody, when you go shopping, do you buy everything at a single store, or are there certain things you go buy at other stores because they cost less?
Yeah, certain things that cost less at other stores.
Yes. So, I mean, if you had a hobby, right? If you were a model train person, I don't know, you might buy a certain thing at one place and a certain other thing at a different place for all kinds of reasons. So what's my point? There's that one problem that deals with guitars and pianos and drums. It wouldn't make sense to say, well, this drum set is cheaper than this guitar. That doesn't make sense. I want to know, okay, at this store, the guitars are cheaper than average, but the pianos are more expensive than average. So if I want to buy a piano, I should go somewhere else. But if I want to buy a guitar, I should go there. All right. I don't know if you guys stayed with me or not on that trip.
I did.
We all experience this exact same thing I'm talking about on a smaller scale, right? Maybe. So, well, let's go to this. Yeah, go to stores that cost less. I understand. But depending on the thing you're going to buy, it could cost less at one store and something else could cost less at a different store. So let's do this. I want to talk about standard deviation real quick, and then we got to get back into probability. Let me turn off my moon. That's no moon. It is a moon. It is the moon. So be quiet, Obi-Wan. There we go. All right, now let's say there's a class that just took a test, right? There's let's say there's two math classes, two stats classes. Let's look at stats class number one. They had a mean of 72 on this test and a standard deviation of 17. Is everybody semi with me?
Mm-hmm.
All right. So the mean is kind of low, but the standard deviation is really big. And most of the time, what this means to a teacher is that there were a few people who did really, really bad, which is why the mean is so low. And that makes the spread really big too. Are you guys semi with me? So for me, I want to give you a little insight. Most tests that I give, the standard deviation comes out to be about 12 or 13, right? So if I get a standard deviation of 19 on something, I'm like, wow. There must be some really extreme grades, right? Most of the time it's going to be extreme bad, unfortunately, like 20s or something. Okay, maybe. Now, let's say that Bob is in this class and Bob made a 75, right? So how did Bob do relative to his class? Well, on one level, you could say he did above average, right? But that's not good enough. I want to know relative to his class, how far above average. So if I want to know how far he did above average, I have to have a way to measure distance in statistics. How far? That means some way to measure distance. I can't measure it in inches or some weird shit. So I measure it in these. That's where the z-score comes in. So I do 75 minus the mean divided by the standard deviation. Can somebody help me out? What do you guys get for that? Uh-oh, they're coming for me. I don't know if you hear that. Some sirens out there. 0.176? I think you're right.
70.76.
Yeah, 176. I like it. Something is going down outside my house. All right. A lot of sirens. All right, so it's positive. It's not very big. Did he score really, really high above average? No.
No.
I like it. How do I know that? Because every step is 17 big and he only made it 3. So he made it 3 out of 17 steps above the average. That's why it's positive, which is good. Now, let's say that Frank is making fun of Bob because Frank made a 92 on his test. And he's like, "Oh, you suck, Bob. You suck." Right? But the mean on the test in Frank's class was a 91.5, and the standard deviation was a 6.2.
Oh yeah.
Sorry? Go ahead.
I think I understand. So Bob got a better grade compared to
Well, I don't
Frank.
know yet. We don't know yet. Frank did make above average, right?
Yeah, by like 0.5.
True. But so we don't know yet how it compares to Bob's relative position.
So he did 1/6. Well, Bob did like
Well, let's find out. So I would do Frank's score minus the mean divided by the steps, the standard deviation, and then I can see. Somebody help me out. What does that come out to be? 1/12. I think it comes out to be. Is that 1/12, Jeff? Yeah. So 0.08. Poor little dude. He did do worse. Oh, well. Poor little dude. So who did relatively better?
Bob.
Bob did relatively better than Frank did, right? So it's not fair to compare your grade with somebody who's in an entirely different class because you have different teachers. The test could have been harder or easier, right? So obviously this was either an easier test or whatever, right? All the students are better in this class or whatever. So relative to his class, Bob did better than Frank did relative to his class. All right, there's one thing I want to talk about for z-scores. So if I'm trying to compare people in different classes, people on different baseball teams, different instruments, I can make a z-score for each one. And then the z-scores are comparable now because they kind of standardize things. Based on the average data there, I get this. Based on the average data in this other class, I get this. Now I can compare those two numbers to see who's relatively better. Okay. Now, I'm going to erase all this. Then there's this idea of if you give me the mean, let's say 40.98, and the standard deviation of 9.32, and I want to know what score is 1.7 standard deviations above the mean? There's a formula here, but it almost doesn't matter. I want to go, all right, so I want to start, now watch this. I really want you to get this. I want to start at the mean. I want to start at 40.98. And I want to go up how many what's?
1.7 standard deviations.
1.7 of these. If I would have said below the mean, you would have just made this minus instead, right? So I want to start at the mean and go up this many steps. Start at the mean, go up this many steps. I mean, that's beautiful. Right. I might be the only person.
Well, then
that
you would multiply whatever it's asking you, whether like it would be 3 standard deviations, and you would multiply that by the standard deviation.
Because think about it. What's the physical idea behind this? If every step I took what was, I don't know, 1.5 feet, how far do I make it if I take 3 steps? 3 times 1.5 feet, right? So that's this many steps, 1.7 times how big each step is. So the math makes sense. And then I almost don't care what the answer is. Who's got the answer there? 56 something?
56.824.
824? Sure. Okay.
Yes.
I like it. So if the average on something was this, and this was standard deviation, and you made a 56, you were actually 1.7 standard deviations above the mean. Right. This is Jeff in grad school making this kind of a grade on the test and going, oh shit. And then the teacher says, good job, Jeff. And you're like, what's going on? I actually did pretty well. Holy crap. All right. Does that help? If you haven't done 2.7 homework yet, this doesn't quite mean as much yet, but there are questions just like what I went over just now on there. And also on the quiz today. Hint, hint. All right, so I'm going to erase all this. Anything else from the homework while I'm still up here?
I had one about number 72. It tells us to use the table that was in number 71. And I was just confused because it says to find the value that is 3 standard deviations above the mean and below the mean. But I don't know which mean they're talking about, because there's the batting average, then there's the team batting average.
All right. So the batting average is specifically for those people, the people they listed. Screw that. You need the actual mean, which is the average of all these. So you want the team batting average. Now, the extra thing that sucks is there's 2 teams. Is everybody sort of with me? You're really not with me if you haven't done this homework yet, but so there's a mean and there's a standard deviation. So you want to use those. Yeah, I don't care about the individual people anymore for number 72. I care about the overall average, the overall mean. This is something like 0.19 something, I don't know. So you would take 3 of these added to this and 3 of these subtracted from this. And then you do the same thing for the other team. Does that make sense?
Yeah, so I was confused of whether we had to pick one person or do both of them, so that helped.
And I was talking to people in the office hours. This says batting average, but it's still for one person. It's not like an actual mean. This would be the mean of everybody's batting average. So that was a bad sport to pick for them, but oh well. I know. All All right, anything else? Okay, all right. So if there is nothing else, we're going to jump right back into chapter 3. Okay, here we go. So back into probability. All right, so last time we actually developed one formula. I don't know if you guys remember this. Right? We figured out this formula here. Now, what I wish I would have done, and I guess I didn't do this because we were kind of running out of time, but let me make, does somebody have their notes from last time? Do you remember what this was? Yes, no, sorry.
Yeah. One,
I'm looking.
it's
Oh.
2,
Two.
41,
Yes.
4, and 39, 4, 6.
What was this here?
Democrat.
Republican.
All right, cool. I like it. So 41, 45, 10, 47, 49, 96. Okay, that sounds familiar. I like it. All right, so that's the problem we did last time. We did several probabilities before we knew any formulas. Remember that? So what that means is sometimes the formula makes things harder than it actually is. And when I have everything I need to count the answers. Probabilities are basically based on counts. Formulas help when I don't have everything to count. So you're going to see today where that comes from. Let's do a problem. I can't remember which problem it was, but let's do a given problem, a fresh given problem. So the probability that somebody is a Democrat given that they said yes. This is like one of the last ones we did. So I want to know the probability that somebody's a Democrat given that they said yes. So how many total people could it be? What do I know about the person?
There is 2 people who said yes who are Democrats.
Okay. Yes. So we'll start with it. I know, what do I know about this person in this problem? What do I know about this person?
They're a Democrat.
No, I don't know that.
They
They
said
said
yes.
yes.
And I want you to remember, how do you say this in English? You say probability that they are a Democrat. So I don't know if they're a Democrat. The probability they're a Democrat, given they said yes. Okay, that's what I'm given. I'm given that they said yes. So how many people am I talking about total?
41.
41. So out of those 41 people, now Anthony comes in. Out of those 41 people, how many match what I'm looking for?
2.
And then, whatever the hell that is. It's going to be like 4.94%. I don't know. Nobody's going to help me. That's okay. All right.
48%.
What is it?
Oh, wait, sorry, wrong answer. 0.0487.
All right. Sounds about right. Now. Let's develop a formula based on what we just did. How do I always do a given? So if I have the probability of A, and let me show you the symbol, because I'm going to do the symbol without thinking about it. That symbol means given, a straight up and down line. That symbol means given. Now I agree that symbol kind of sucks because it makes it look like a fraction. But it just means A given B. Where did the bottom come from? Why was the bottom 41?
It's the total amount of people that say yes.
Good. So the bottom is based on the given. So the bottom is based on B. So then the top was 2. And what is it about those 2 people? They are
Democrats that said yes.
Yeah, they're Democrats that said yes. They're Democrats and they said yes. So that is the formula for any given problem. Now, again, I want to remind you guys, we created the formula after we did a problem. That's kind of crazy. I love you guys. I love you guys. I love you guys. I really want you to get this. The basic idea of a probability never changes. It's the number that matches what I'm looking for divided by how many it could be. Why were we able to do this before we even knew the formula? Because the number of things I'm looking for divided by how many it could be was easy because I could count everything. So if I'm not given this much information, then I might have to use the formula.
Can you do it using the formula then? Like when
We will.
Okay.
We will. And actually, we can do this one. So watch this. We can do this one. It just gets a little more disgusting. What's the probability of a Democrat and yes divided by, right? Democrat and yes divided by, divided by yes. So Democrat and yes would be 2 out of 96. Probability of yes would be 41 out of 96. And if you throw in the calculator, or if you just realize the 96s cancel, so you get 2 out of 41, which is what we got there.
Isn't the total number of yeses 41?
Yep, that's what I said.
Oh, I'm sorry. I was looking at the wrong thing.
Okay. All right, let me see.
So does that mean that the given and the word and are the same thing? Because there's
No,
okay.
because the probability of A given B does not equal the probability of A and B. The probability of A given B equals this divided by this. So are they related? Yes. And I want you to realize why. If I'm given they said yes, what's the only way they could also be a Democrat? Could they be here? If I'm given they said yes, could they be any of these guys?
They might be in the
They're
region.
Democrats. Could they be these guys? No.
Nope.
If I know they're one of these people, they can't be those people, can't be those people. So they must be Democrats and yes, they must belong to that. So and given is connected. You can see it in the formula, but they don't equal each other, right? The formula isn't that. What's that? Okay, maybe. All right, now. There's one more formula we have to do. Can somebody tell? We have a formula for or, we have a formula for given.
Someone asked, does and have a formula?
Look at that. Somebody's ahead of me. That's the line. Yeah. It does have a formula. In fact, I sort of already wrote it down, but we're going to find out here in a minute. So let's talk about and. Maybe. All right. So let me cut to the chase. This kind of sucks that it has to be plural. What I'm about to say is plural. Does anyone remember the 2 times that the space shuttle has blown up? You guys understand what I'm saying? The space shuttle It's been discontinued, that program now, but it blew up twice. Do you guys know that?
Challenger?
Yeah, there was the Challenger, and it also started with a C. One was in 1986 when Jeff was 14 and he was in English class, and he remembers this because they came over the loudspeaker and he started crying when they said it blew up. I feel better now. Okay, but it was horrible. And then the second time, it really sucks. There was a second time. I think it was, I can't remember now even what year it was, to be honest. 2000 something. I've lost track. But all right, stay with me. The first time it blew up, what the problem was, there's a gas line. This is kind of oversimplifying things, but that's all right. This is not an aerodynamics class. There's a gas line with what's called O-rings. I'm not going to go too deep into this. Don't worry. We're not going to become an engineering class. What the O-rings did was they made sure the gas flowed in one direction. Would it be bad if the O-rings failed?
Yeah.
Hell yeah. You don't want gas flowing the wrong way. So, normally, for the sake of convenience, let's say that normally an O-ring has a 1% chance of failure. Why would you want multiple O-rings here?
To reduce that 1%.
Yeah, so the idea, if I want to know, if I put two of these in a row, can I do the same thing as the OR does, which is add these together? Why would that not make sense? Of course I don't add them together, because I have multiple of them to make it less likely the probability that the whole thing fails. So this one has a 1% chance of failure. This one has a 1% chance of failure. What percent of the time will they both fail? Right? So 1% of the time, these will fail. 1% of those times, these will fail also. 1% of 1% is multiplication, right?
Yes.
1,000th of a percent. Wait,
Yeah, so
100th of a
101
percent.
101. Sorry? Say it one more time.
Huh?
So another way you can do this is 1 out of 100 times 1 out of 100 is 1 out of 100, right? So it'll be 1 out of 10,000, right? Otherwise known as 0.01%. Let me stop for a minute. So if I put even more of these in a row, I'd have to multiply them all out. So what am I trying to say? OR is basically add, right? Probability of A or B is probability of A plus probability of B is basically addition. Because you're adding in more options. That's why the OR bouncer is the nice bouncer. It adds in more people. And is basically multiplication. It's multiplying these small numbers, which makes the result even smaller. So if, has anyone ever done this? You have the final the next day. So you set the alarm on your clock, and you set the alarm on your phone, and you ask your mom or whatever living situation you're in, you ask them to come in and wake you up. Has anyone ever done that before? Have multiple ways to wake up? Yes, we all have. Why do we do that?
Just in case it doesn't go off on our phone or something.
It's really quiet. In case
Our phone doesn't go off or something.
Yeah, in case any of those don't work, right? We're trying to decrease the chance overall that I don't wake up. Contingency plan, right? So if I have 3 alarm clocks set, this is my alarm clocks. They look like I don't know. They look like a pig on 2 legs. If each one of these has a 1% chance of failure, it's just like this. Overall, it would be 1% times 1% times 1%. Now we're talking crazy small chance that they all fail, right? Okay. So what am I trying to say? I don't know. I forgot. So all of that was just to kind of prove to you that and basically means multiply. Let me make sure you understand what that means. Multiply. Where or basically means add. Why do I say basically? Because or, just to remind you, is one plus the other one minus any that I counted twice. It's got a little adjustment to it, right? But it still is basically add. But it's got that little minus on it in case you counted anybody twice. Okay, maybe. So this is going to have a little adjustment on it also. So now watch this. Here's where I'm going to get the actual equation from. Doesn't and show up in this equation we just did? This is what I said earlier when I said I already wrote the equation down. Isn't there an and right there?
Yes.
How do I solve for this? How do I get that by itself? What do? I want to get this by itself.
Multiply it.
Multiply by this business, right? Multiply by peanut butter. Multiply by peanut butter. So I get probability of A and B equals the probability of B times the probability of A given B. Times. Now that makes even more sense that showed up. Because we saw earlier that and should lead to multiplication. Now on this and this and this, it would be that percent of that percent of that percent times. Okay, maybe. This also, now watch. Let me see if I can really get you on my side with this. Let me see if you guys can handle this. All right, now watch. Just stay with me for a second. There's one formula for this. There's a slightly, it's the same formula, but let me see if you guys realizing this is true, right? This is true. What's the formula for this then? How is that different? What's going to be on the bottom if I'm asking this? B given A.
A.
A, I love it. So now if I multiply up, stay with me. If I multiply that up, I get this. So you've got two, they're both the same thing. I really hope you understand because A and B are interchangeable. So that's all it's saying. They're interchangeable. Okay, maybe this, maybe not. Okay. You want some concrete examples instead of O-rings and
Yes.
peanut butter?
Yeah.
Yes.
Really, you do? Okay. I guess I'll do it. I wasn't planning on it. Obviously, that's a lie. All right. So that's the formula. That's the big thing to get down. They're both the same. I really hope you guys understand they're both the same. Sort of like, oh, go ahead.
Are there only two formulas then for probability and given?
And, given,
And or?
and or. There you go. There's three.
Okay.
That's right. And the reason I really want you guys to understand the reason that these are interchangeable, if I said Frank and Jim, isn't that the same thing as Jim and Frank? So that it, right? I don't know. It's kind of like why these can switch around. All right. I don't know.
So just for clarification, when you multiply the probability of B to the probability of A divided by B, it turns to the probability of A and B?
Listen. That is not divided by, that's given. Completely different. You with me?
Yeah.
But yes, what you just said, you're right. And let me see if I can't give you a concrete example of why that is. All right, I'm gonna go to the standard. I got 4 red poker chips, 6 green poker chips, and 8 blue poker chips. Okay. Exciting. And I'm going to pick, now watch this. So first off, let's do it real quick. I'm going to pick one chip. What's the probability I pick a green chip? Start off nice.
6 out of
18.
Let me make sure that's a G. 6 out of
18.
18. All right, about 33%, right?
Yep. Okay.
All right, so that's boring shit. So let's do this. What if I pick 2 chips? And I got to tell you how I'm going to do it. I'm going to pick 2 chips without replacement. What the hell does that mean, Jeff? So that means I'm going to pick a chip, I'm going to look at it, and then I'm going to throw it away. So everybody with me? Okay. Or I pick a chip, I look at it, I feed it to my little brother. Right? That explains a lot about. Anyway, sorry. Hey, Jim. Like he watches this. All right. So if I pick 2 chips without replacement, I want to know the probability that I get a green chip and then a blue chip. So watch how this works. What percent of the time will the first one be a green chip? We already know that. We've already done that, right?
Yes.
What is that?
33%.
Yeah, so do the whole thing. 6 out of 18. All right. And means times, because 6 out of 8, 6/18 of the times the next one's blue. All right, now watch. I just took a chip out, right? I'm going to throw it away. How many chips are in the bag now?
So it would be 8 out of 17.
Yes, there's 17 chips left in the bag, and but there's still 8 blue chips. Now just throw all that in the old calculator. So and means multiply, because 6/18 of these times, both of these will happen. Of means multiply. So you just multiply that through. I have no idea what you're going to get. Well, I sort of do. You get about 16%. Is it really? I don't know what that is. Does that make sense, Jeff? Yeah, it does. I think you get about 16%. Is it 17%? I don't know.
It's 16%.
Holy shit. What did I do? Oh, I see what it did. All right. Yeah, cool. So let me be even more precise here. I got to be careful. Let me come back to what I was talking about yesterday. We're going to take all of our, I know I didn't do it here because 1/3 is who cares, but this is 0.1569. And then you can make it a percentage if you want to. Okay. All right. So again, I really want you guys, I hope that the whole thing about the O-rings and the alarm clocks, meaning you do multiple things to make sure the overall thing becomes less, it led to us multiplying, and means multiply. Why did that number change? Because I said this, right? So what if I do, let me pick, let's pick 3 chips. But this, I'm going to do it with replacement. What the hell's all that mean? I don't know. And I wanted to probably get a red, and then a green, and then a green. Yeah.
So would red be 4 out of 18, and then green would be 6 out of 18, and then green again would be 5 out of 18?
No, careful, because I'm doing it all with replacement. I'm not losing anything. I pick a red one, I throw it back in. I pick a green one. I throw it back in. I pick another green one. Nothing changes because I keep putting it back in. Everything resets. Pick a red, put it back in. Pick a green, put it back in. So I want red, put that probability, and times. Green, put that probability, and times. Green, put that probability. Let's see, what's that going to be, smart boy? I don't know. 2 point something? No. Yes, 2 point.
4.6.
I have no idea. 2.3? Oh, 247? Oh, that was close. Sorry. So 2.47%. So what would that look like if I did the same thing, but I did it without replacement?
Well, at the bottom will be 18, then 17, then 16.
That's true. And then somebody else just had the same, so I want to do this again, but without replacement. A probability of RGG. I should have done RBG. Dang it. All right, it doesn't matter. Just out of respect. So this would be a 4 out of 18 chance I get a red chip, and then I throw it away. There's still 6 greens, right? But now there's only 17 chips. Is everybody? Every time you take a step, you've only done one thing. For some people lose more than one. I don't know how they do that. I've only picked one chip, so there's another 17. So now what's going to be on the bottom here? I think the Keisha already said
16.
16. And how many green are left?
5.
5, because I took one out the second turn and threw it away. So I don't care how long this gets. It's going to be relatively easy. Just keep multiplying. I don't even know if I want to try that one in my head. One fourth, 1/3, 1/12, 5/17, 1/3, 1/36, 1/6, 1/6.
The only question that I have is, what does the 4, 6, and 5 stand for? Like, are those just arbitrary numbers you picked, or?
Definitely not.
Okay.
Right? Or else we wouldn't all get the same answer. There should be no way for me to grade anything. So what did 4 relate to? That's how many whats?
How many chips?
How many red chips?
Oh, okay. So
This
you.
is the question.
Oh, I see. My bad.
On red chips, and then a green chip, and then another green chip. So the real question is, why was it 6 here, and then it became 5 there, right? Why? Because what did I do right before this? I picked a green chip and I threw it away. So of course there's one less green chip, and there's one less chip. All right. And somebody told me, is that an answer for this one? 0245?
Yes.
Yeah.
That's neat. Oh, okay, good. Yeah, that's right. So I really want you to understand, if it's without replacement, the bottom is always going to change. The top will only change if it makes sense, right? I keep losing a chip. I lose a chip. I lose a chip. But the top only changed here because I lost the same color. All right, I don't. All right, it's not that crazy. It really isn't. Okay. Do any of you guys, anybody really suck at cards? Do you know how cards are basically, how many suits are there in a deck of cards? Do you guys know? There's diamonds and hearts.
4. Spades.
Clubs, spades.
There you go. So it's 4 suits. There's two colors, right? Black and red. How many total cards are there?
52.
50.
52. Right. How many? So there's there's gonna be 4 of each card. So if I said, what's probably I pick a king out of a deck of cards, what would that be?
4 out of 52.
Exactly. 4 out of 52, or 1/13, or whatever the hell that is. So if I pick 2 cards with replacement, what's the probability I get a king and then an 8? So watch what I do. I say there's 2 things and multiply. So one thing and then the other thing. So it's probably get a king.
4.
$52.
Good. So probability can't be bigger than 1. So it's got to be some ratio. And what's probably get an 8.
4 out of 52.
Yeah, kick ass. It's kind of boring because every card's the same probability if you look at it just like that. So that'll be whatever that comes out. What does that come out to be? 1/13 times 1/13.
.0769.
Oh, sounds okay. Yeah, exactly. Some of you guys might have learned some of this stuff before. So, but if I do it, so let me ask you this. All right, let's get more interesting here. All right, let me remind you a couple things. Let's go back in time for a second. So this is A, so B. What's the probability I pick a king given it's a club? All right, so how many? So there's 4 suits, 52 cards. How many clubs are there?
4.
There's clubs, spades, diamonds, and hearts, right? So how many clubs are there? Yeah, 13 clubs. And out of those 13 clubs, how many are kings? Just one of them. Now, how does that compare to this? Did that change the probability at all? I was trying to be a 13, by the way.
No.
No, it didn't. I really want you guys, this is huge. We're getting into a kind of a different idea here. If I know the card is a club, it does not change the probability it's a king at all. But watch this. How many, do you guys know how many face cards are there? How many cards have a face on them? There's kings, so that's 4. Queens, that's 8.
16.
And then the jacks, that's 12. So there's 12 cards that have a face on. So there's 12 face cards. So what's the probability that I get a king given it's a face card? So out of 12, out of the 12 face cards, how many are kings?
4.
4. Now, did that change the probability at all?
Yeah.
So the probability that a card is a king is affected by whether or not it has a face on it, right?
Doesn't a king always have a face on it?
Yes. So if somebody told me I'm looking at a card right now, what's the probability it's a king? 1 out of 13. But then they say it has a face on it. What's the probability that it's a king now? 1/3 chance. Yeah. So if you were like betting, putting money down on what kind of card it was they picked, and you somehow could tell it had a face on it, like you could see in the reflection and behind him, like, oh, I could see it has a face, then there's a much higher chance that it is a king. I'd feel better about betting on the king than I would if I didn't know shit about it, right? But if somebody said, I have a card, oh yeah, I'll tell you it's a club. Does that change how you feel about a bet that it's a king? No. Knowing it's a club does not change the probability it's a king. I'm exactly as in the dark as I was before. I really want that to make sense. So somebody's got a card and they say it's got a face on it. Now I feel a little better about it possibly being a king, correct? Because it can't be a 7, it can't be an 8, can't be a 9, can't be a 2, can't all that stuff. But if somebody's holding a card, they say it's a club. Do you think it's a king? I'm like, that doesn't do anything for me. It still has a 1 out of 13 chance. I don't know. I don't know if you guys are with me at all. So the idea we're talking about right now kind of makes sense. The name of this. Would you say that the idea of face cards and the idea of kings, would you say that they, let me see how I want to say this. Would you say the probability that it's a king depends on if it's a face card or not? Does the probability it's a king change if it's a face card?
Yes.
It does. So doesn't it just make sense then that I would say the probability it's a king depends on whether it's a face card or not?
Mm-hmm.
Because it changes if it is, right? Do you guys get that idea? Does it care if it's a club? Does the king give a shit about whether it's a club or not, the probability? No, it doesn't give a shit. So I would say the word we use for this situation, we would say that those are independent. Knowing one happens does not change the probability of the other one. Doesn't the word independent make sense there? If I know it's a club, does it change the probability it's a king? Nope. But if I know it's a face card, does it change the probability it's a king? Yes. So we would call this dependent. Holy shit. So if I ask you, are A and B independent? Notice how slowly I am talking right now. This is a huge clue. I found a clue. To check to see if I say, are A and B, whatever they are, king and face, whatever, independent, what do you have to check? You got to check and see if the probability of A given B, let me put this down, if the probability of A given B equals the probability of A. I really, really, really want to make sense. If B happens and A doesn't give a shit, it stays the same, they're independent. I really, really want that to just make sense.
It does to me.
We'll find out. The proof is in the pudding of the test in the quiz, so we'll find out. All right. You cannot answer this question with a paragraph. Well, some B's could be A, and then, no, bullshit. This is only answerable through math. You have to check these. And of course, this whole idea of independence is, do they affect each other? And the only probability we can calculate that shows how two things affect each other is the given. So if I do this and it ends up the same, the probability of A given B, if it's the same as the probability of A was before, then that did not do anything. So they're independent. Then let that just make sense. Okay. All right. Last thing, and then I'm going to bring up the little handout, the little probability handout. So real quick, when we did this, if I did pick a king and then an 8 and then a 5 and whatever, right? So I'm going to pick like 3 cards. This would be a 4 out of 52 times. It doesn't really matter. 4 out of 52 times 4 out of 52. Blah 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 blah. Right? Let me be more careful. All right. What if I do it without replacement? What would that become? Without replacement, probability of a king, and then an 8, and then a 5. What would that be? The king is still 4 out of 52. It's without replacement, so what happens here for the 8?
4 out of 51.
4 out of 51.
4 out of
4 out of 50.
4 out of 50, I like it. Yeah. And if I added one more, let's do another 8. All right, let's see if you guys can do that. If I add one more card, say, all right, I want an 8 again. What would that be? I might be. How many
3 out of
8s are left?
49.
Say again, sorry.
3 out of 49.
Good. 3 out of 49, because I already picked an 8 and threw it away. Okay. Right. That's basically a little review of what we just did. Now watch this. All right. If I have a problem where, watch this. So I know that 11% of Americans are left-handed. I think we did that last time, right? 11% of Americans are left-handed. How many Americans are there?
365,000 or something. Do you need the exact? I can look it up.
If so, then unfortunately, none of us are left. I don't want to bring everybody down, but there's been more COVID deaths than that. So we're all gone.
Million. No. Sorry.
There you go. Yeah. I think it's like 330 million at the moment, somewhere around there. So I really want you to understand. Why was this one relatively simple? Because how many total cards are there? 52, right? Can you imagine? I really want you to understand. Can you imagine making the fractions for this problem where the bottom is 300, I think it's 332 million something. Oh my God. And what if I pick 4 people? All right, now I'm really trying to. So isn't the population on this thing, isn't it big? It's got a big population, correct? What about that problem over there? Is it a very big population? What's the population in this problem?
52.
52. Is that a big population? No. So the beautiful thing that we can do when I have a big population is I don't have to make fractions. So watch this. If I pick 4 people, what is the probability that they are all left-handed? So I got 1, 2, 3, 4. Does it use the word and anywhere here? No. But what's another way to say this? The first one's left-handed and. The second one's left-handed and. And means multiply. So what's the probability the first one's left-handed? 11% chance. And the next one, and the next one, and the next one. I don't have to set up the fraction because I had a big population. I really want you to get that. So, and then whatever the hell that is, I don't know. What's that going to be, Jeff? 1 3 3 1 1 4 6 4 1. Is it 0.1 2 3 1 5 roughly? I don't know. That's a major guess. I have no idea what that is. Is anyone going to help me? Oh, you probably don't even know. Do you know how to read that? Oh, I got it right. Holy shit. Almost. I was off by a 0. Damn it, John. Was I? No, I'm right. That's exactly right. I'm sorry. I'm excited. I love it. Okay, beautiful. Somebody's asked a perfect question in the chat. Okay, I love you guys. You guys are too awesome. Stay with me now. Let's just make this easy. Let's go ahead and make the population of America 300,000. I love it. It's actually way bigger than that, right? But 300,000 is a nice sample. I mean, a nice population size, right? Let's say that 300 out of 300,000 are left-handed in this certain little island. What is 300 divided by 300,000? What's
3
300
over 3,000.
6. Oh, sure. But go ahead and take it all the way out. So it'll be 0.001. Is that right?
Yes.
Yeah. Now watch this. What if I take one of those people away, one of these left-handed people? Won't there be 299 left-handers out of 299, 999? Somebody do that for me real quick. I'll do it too. Again, you have to know how to read it. Remember the times 10 to the, do you guys remember that? Are you guys getting this? Is anybody doing it? 9.96, blah, 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 blah.
Yeah.
And you have a little E, you remember that? You have an E, -4, that means 9.96 times 10 to the -4, which means move the decimal 1, 2, 3, 4. Do you guys understand how these are the same number? Do you guys see that? 99.6 is the same as 100, basically. Do you guys see how they're almost exactly the same number? Doesn't that make sense? If I change this by 1, is that going to change this by much? No. And now imagine that the actual number is millions. Right? Millions for America. So the bigger the population is, the less change it would make to lose 1. So that's why I can just put the pure percentage over and over and over again. I don't have to keep track of the fractions. I know this is a lot to come at you. I know. But oh well, that's how this works. Right? So if the population is large, I don't have to make the fractions. I could just use the percentages, which is really, really beautiful. So let's take a look at this sheet. And then we'll call it a day. What time is it? Oh, we got plenty of time. Look at me. Why did I feel like it was later? Oh yeah, because I started at 12:30. Okay. Mouse, wake up. Okay. So on Canvas, I think I showed you this yesterday. There is a probability worksheet. It's actually got 2 sides to it. One side, did I put it up here, Jeff? Yes, you did. One side, it says, this side in class. You gotta love that stuff. And then the other side is a practice quiz. I called it a double quiz before, but don't worry about it. It's just the practice probability quiz. All right, so I will have an answer key for this, but let's look at this side today. Is anybody not able to access this? Can you all go get this? All right, I'm going to assume that's a yes. Let's see what happens if I do this. All right, so everybody go get that sheet and start working on it. Let me pull it up here. Where'd you go? Oh yeah, it's going to be back here. are you? Oh, that's this. Okay. All right, let me do this. Do, 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 do. All right, there we go. There we go. All right, so is everybody working on this bad boy here? Okay. Dadgummit. All right, let's see. I'm going to sort of do this with you here. I can add. Is that right? Oh yeah, I forgot about that. Oh, well, we'll do it together. So here, I haven't let you guys work together in a while, and I know you guys just love when I do that. So here in a little bit, I'm going to put you in the breakout rooms. So some of you can awkwardly try to talk to people that won't talk to you. Hopefully everybody talks to each other. That would be great. That's the way things work really well. If you have a room full of duds, just call me in when I do that. Here, I'll stop recording. Let's do this. Then we'll do this. All right, let's take a look. So let me get rid of that thing. You guys can see the worksheet now, right? I believe. So up here real quick, we kind of did this one together. If you do it in the calculator, you get 7159. Is that right? Yeah. Is that cool? You can make it a percentage if you want to, right? It's up to you. What's probably their business major? So how many business majors?
92 out of 176.
Yeah, 92 out of 176. What's the only problem in this selection here that's not going to have a 176 on the bottom?
E.
It'd be part E. Because that's the only one where I know something. So I can throw some people out. So if you do 92 out of 176, you get 0.5227.
Yes.
Coolness. Then we hit our first OR. So I want them to be a computer science major or go to Grossmont. So the way I do this is I say 126 Grossmont students, how many computer science majors have I not counted yet? 11. So it'd be 126 plus 11. Now, if you want to do something more like the formula, I have 126 Grossmont students plus 73 computer science majors minus 62 that are both, right? But I kind of would say, why the hell would you do that? That's crazy. Because you could just do 126 Grossmont plus 11 that I haven't counted yet, because that's exactly what this is, right? Does any of that make sense? Are you guys
Yes.
with me? Or, all right, so you get 7784,
Yes.
I believe. I believe I can fly. All right. This one always trips people up because people try to use the formula. The formula makes part D so disgusting when it is so simple and is very restrictive. It will make the numbers smaller than anything else because you have to meet all the requirements. How many students meet the requirements of being a math major and a Cuyamaca student?
2.
2. Only 2 do both. Only 2 are math majors who go to Cuyamaca. There's only 2 out of 176. And that you get 0.0114, I believe.
4.
Yeah, I'm not doing these in my head, by the way. I divided them earlier. I won't take credit for this. So part E is the only one where the bottom's different, and you have to get used to the bottom comes from the second piece. The bottom comes from the given. I'm given they're a computer science major, so I know I'm talking about these people. Out of those 73 people, how many match what I'm looking for?
C2.
62. There's no way the top can be bigger than the bottom in a probability because that would be more than 100% chance of something. I don't know what that would mean, right? So what do you get when you divide those? Have I done that yet? Yes. Look at me go. I get this. You guys with me? Because again, find the probability that the person is a Grossmont student. So I don't know if they're a Grossmont student. Find the probability they're a Grossmont student given computer science major. So I know they are a computer science major, and that's why I know I'm talking about 73 total people. Okay, maybe. So are being a Grossmont student and a computer science major independent? This is where I'll get people say, well, you could be a Grossmont student and but you don't have to be. No. You start writing a big paragraph, you're wrong. You're wrong. Stop. You've already done the work to answer part F. They're not independent since they're probably Grossmont students. There you go. That's it. What was the probability of being a Grossmont student from the beginning? About 72% almost, right? You guys with me? What does it become? Does it change if I happen to know they're a computer science major? Does the probability change? Yes. So the answer here would be no, they're not independent. The probability of Grossmont student does not equal the probability of Grossmont student given computer science. Oh my God. Then put underneath the numbers 0.7159 does not equal 0.8493 NITO. So I could be even more specific. Knowing they're a computer science major increases the chances they're a Grossmont student. I like it.
So if
Sort of
that
like,
question were on a homework assignment, do you want us to do it like with a formula showing that, or would you mind if we like wrote it out? If like
I'm not. Go ahead.
So if we got this question on an assignment, would you prefer the answer being like we write out an explanation, or would you prefer it if we did it how you just wrote it, showing us?
No matter what your answer is, it's got to include what I just said. And what I just said is enough to answer the question. Does that make sense?
Yeah.
So to answer this kind of question, you have to include what I've written.
Okay.
And what I've written is all you need to show. So if you want to write more, go ahead, but you don't have to. Yeah. Does that make sense?
It does.
Okay, because I'm just concerned. Some people kind of talk themselves out of the answer. They start writing, well, you could be a Grossman student and the thing. So I don't think it's I'm like, no, stop. It's a completely math question. Are these two numbers equal? That's really all it comes down to. All right. I like it. What time is it? I don't want to keep us too late. So how about this one? This one should be pretty straightforward, right? We would all like to do all kinds of things to some politicians. So this is relatively benign, putting them in a haunted house. What's the probability that I pick a Democrat out of this group of people?
7, 19, 20, 21,
7 out of
21.
21. I love it. So about 33. So 0.33 to be official, right? And what's the probability they're a Republican?
12 out of 21.
12 out of 21 is crazy. Whatever the hell that is. I don't know. 4 7. So 0.5714. Is that right?
Yeah.
I know my divided by sevens. Sorry, nothing to be proud about, Jeff. All right. Now we're going to pick two people with replacement, which means nothing changes as we go through. So I know I'm picking two people. So I'm going to put one person and times another person. So I want the first person to be an independent. What's the probability the first person is an independent?
2 out of 21.
Good, 2 out of 21. And they're so happy. I take them out of the house. Oh, thank you. And then we throw them back in the house. And then I pick somebody else. What's the probability that that second person is a Republican?
7 out of 20.
20.
So many things are happening right now. I put that first person back in the house, right? Because I'm doing it with replacement. So how many people are still in the house?
I'm at
1.
And one. And how many of them are Republicans?
12.
12. Right. So then it would be whatever the hell that is. It's like 0.056 something maybe.
317.
What is it?
Point 0544.
0544. I like
got
it.
it.
Okay.
Oh, I multiplied.
And then two Democrats. So again, it's still with replacement. So the first one being a Democrat would be 7 out of 21. I throw him back in or her back in. And then the second one being the Democrat would be 7 out of 21. Or them, right? Whatever their preferred pronouns are. And then I just have to multiply those together. Is that cool? So they're both Democrats. So they're both going to have the same probability because I'm going to reset things. I'm not going to take the first person out and let them go home. I'm going to put them back in the mix. So this one comes out to be 1 1 1 1. Is that right? Is everybody cool with that one? You guys okay? And now notice, oh, here's some chats coming. Yep. Okay. I love to do this kind of thing. See how these are the exact same questions? Exactly the same questions, just now without replacement. So independent first, 2 out of 21. This time we let them go home. Now, somebody was jumping the gun earlier. You come in now. What's probably the Republican, the second person?
12 divided by 20.
12 out of 20. I love it because I lost a person. And that's going to be about 0.059 something. Maybe.
0571.
Darn it. 0571? You sure? Is it?
Yeah.
Really? Oh, yeah, it is. How about that, Jeff? You could have done that. Oh, well, too bad. And I really want you to see. Do you see how I could just sort of like kind of cheat off of myself? And I love to do this because I let you. So First Democrat, 7 out of 21. Let them go home. What's probably the second one's a Democrat?
6 out of 20.
Good. I lost a Democrat. I lost a person. Kick ass. And that one's easy. All right. What time is it? Ooh, it's going to be time. So let's do this. Let's finish this one up first thing next time, I think. Because we're coming up on a hard stop and I didn't give anybody a break. And oh my God. This, again, this whole thing is completely up to you. You can try this if you want to. I'm going to post the answer key up. All right. And don't forget what's happening today. What's already actually just opened.
Quiz.
Quiz. I love it. So there's the quiz. It's ready. It's not due until Friday morning, but it's going to be timed again. So the minute you open it, you have a certain amount of time. I can't remember exactly how much I gave you. You'll find out.
Probably this
All right.
part 3, right? It's not on the quiz. It's just
What's that? Sorry. Yeah, this is just on chapter 2. This does not include this.
Okay.
Yeah. Yeah. So you got time on chapter 3 homework. You want to focus on chapter 2 for sure, so you can get that quiz done.
You said in the review for that that video you posted about the answers that it was only going to go up to 2.6. I don't know if
Oh shit. So that was Jeff from last semester. Thank you for telling me that. I didn't go back through that. That was Jeff from the past. That was this semester. We're a little ahead of my class last semester. Good job, guys. So 2.7 will be on the quiz today.
oh,
I'm really sorry. I completely forgot that happened last semester. I think I mentioned to you guys that was a video from last semester.
yeah, that's why I wasn't sure if you were still doing the same thing or not.
I'm
Okay.
sorry. Yeah, listen to present day, Jeff. I forgot about that. That's my fault. I'm sorry. Okay. All right, guys. So let me know if you have any questions. Otherwise, you're free to go anytime.
So you have the quiz for today locked for I think the 26th. So I have up until the 26th to do the quiz.
Yeah, the due date is this Friday. That's when it's due.
Okay.
You have it still this Friday morning. I just figured that'd be nice. See what that feels like. I don't like it so far, but we'll see.
Okay.
Okay.
So 3 o'clock.
All right, guys. I'm going to head out. I'll see y'all next week. Have a good weekend.
You.
I will do that.
Professor, I just had a quick